In this tutorial, I'll quickly walk through homework 7.1, which is a simple Brayton cold air standard problem. In this problem, we're doing the Brayton cycle as an open system. So our equipment consists of a compressor, heat exchanger, turbine, and another heat exchanger. This could be a gas turbine power plant, be a simple application for this. The heat exchanger between the compressor and the turbine has heat transfer in, and between the turbine and the compressor going the other way back, it has heat transfer out. And we've got some mass flow rate going through the system. If I label the states, typically label starting at the inlet to the compressor state 1, then state 2, state 3, and state 4. Let's draw this on a PV diagram. I have an isentropic compression process from state 1 to 2, so my compressor is isentropic. Then I have isobaric heating in my heat exchanger, my QN. And then isentropic expansion in my turbine back to my original pressure. And then finally isobaric cooling in the heat exchanger. There's my simple 4-process heat engine. Given the temperature at state 1 and the pressure at state 1, RP, which is my pressure ratio from state 1 to 2, so RP is defined as P2 over P1. So rather than give a compression ratio as we did with the Otto cycle, we're going to give a pressure ratio for the cycle. And if you look at the diagram, it should be clear that that also equals P3 over P4. And then I'm given a cutoff ratio, RC, which is defined as V3, in this case, over V2. All right, now I should be able to calculate everything. Rather than giving the mass flow rate in this problem, I gave a volumetric flow rate in cubic meters per second. And the mass flow rate equals the volumetric flow rate over the specific volume. So in this case, the volumetric flow rate is also, should say, given at state 1, because the specific volume changes different places. So that would be a V1 that's given. In that case, I can find m dot if I can find the specific volume at state 1. So let's start there. Specific volume at state 1, I could use the ideal gas law, which would be RT1 over P1. And for air as an ideal gas, R is 0.287 kilojoule per kilogram K. T1 is 300 K. And P1 is 100 kPa. And I have to make note of what a kilopascal is. So 1 kilopascal is 1 kilonewton per meter squared. So getting a little closer to if I multiply times meters, divide by meters, then I'll get a kilonewton per cubic meter. Kilonewton meter per cubic meter. And a Newton meter is a kilojoule. So finally I get 1 kilojoule per meter cubed is a kilopascal. When I do that replacement, then the kilojoule cancels and my K cancels, and I end up with units of cubic meters per kilogram. And doing that calculation, I end up with 0.861. So if I wanted to find the mass flow rate through each component, I could use state one, the volumetric flow rate at state one, which was given as 5, divided by the specific volume that I just found. So m dot equals 5 divided by 0.861. And I will get, this was in units of cubic meters per kilogram, and a volumetric flow rate, cubic meters per second. 0.861 cubic meters per kilogram. And if I take 5 divided by 0.861, get 5.807. Kilograms per second. And that's actually asked for down in, okay. All right, let's go now to the specific states. Let's start with state one, the specific enthalpy at state one. With a cold air standard, I can use definition of the enthalpy being calculated as the specific heat times the temperature. So it's state one, and I'm assuming that CP equals 1.0045 kilojoule per kilogram K. That is at 300 K. So I'm going to use a constant value at 300 K. That's by definition for cold air standard. So my temperature is 300, 1.0045 times 300. You get 301.35. Now, normally we would write delta H equals CP delta T. And so any constant could be added to that. We'll always be using differences. So in the homeworks, I always assume that that constant of integration, we had some constant Z, then you could write the enthalpy offset by some constant because we're doing an integration. But in this case, in the homeworks, I use that Z equals 0. Right, determine the temperature at state 2. So this is an isentropic compression process. So we can, for constant specific heats, we can use the relationship that, so S equals a constant, that T2 over T1 equals P2 over P1 to the K minus 1 over K. In this case, along with a specific heat, K equals 1.4. So we've got P2 over P1 is our pressure ratio, RP, to the K minus 1 over K, which should simply be 10 to the power 0.4 over 1.4. And when we put that in a calculator, we get 1.931. And then multiplying by T1. So it's 300 times 1.931, which is 579.21. All right, then moving on to determine the pressure at state 2. So at state 2, we were given a pressure ratio, which is 10. So it will just be 10 times the pressure at state 1, which was given us 100 kPa. So P2 equals P1 times RP, or 100 kPa times 10. So equals 1,000 kPa. Again, our pressure ratio, RP, is defined as P2 over P1. Okay, and then finding the specific enthalpy at state 2, same as before, just multiply the temperature times Cp. That will give us 301 point, or temperature state 2, 579.21 times 0.0045, 581.82. Just equals Cp times T2. Temperature at state 3. Now we're given a specific volume ratio. In this case, since the specific volume ratio is given and pressure is constant, we know that the specific volume ratio is the same as the temperature ratio. So RC is the same thing as RT, which is just T3 over T2. So we have that T3 over T2 equals RC, so T3 equals T2 times RC. And in that case, T2 is 579.21 times the strange number 2.43864. And I get 1418.84. The next question is to find the pressure at state 3. If we look at our PV diagram, pressure at state 3 is the same as pressure at state 2, which we already calculated. So it'll be 1,000 kPa. Noting that P3 equals P2 by definition, it's an isobaric process. Then determine the specific enthalpy at state 3. That will just be equal to Cp times T3. Noticed a slight discrepancy in my T3, so let me just correct that. When I did that again, 579.21 times 2.43864, I get almost what I had written there, but 1,412.48. And then multiplying that times 1.0045, I get 1418. 0.84. I think I jumped ahead and looked at the answer for the enthalpy. Okay, let's move on then to temperature at state 4. So the entropy again is constant from 3 to 4, and so the pressure ratio is the same as for the pressure ratio from 1 to 2. So I can use that same isotropic relationship just like I did for process 1, 2. So I can write that as T4 over T3 equals P4 over P3 to the K minus 1 over K. And in this case, this is equal to 1 over RP to the K minus 1 over K. And so finally I have T4 equals T3 divided by RP to the K minus 1 over K. T3 was 1412.48. Divided by 10. So the power 0.4 over 1.4. This gives us 731.59. And the pressure at 4 is equal to the pressure at 1. If you look at the PV diagram, since process 4.1 is an isobaric process. And then again, H4 equals the specific heat at 300 degrees, since we're using cold air standard, times T4. And when we multiply that, we get 734.88. Which is 1.0045 times 731.59. We already found the mass flow rate, and now we want the power output for the engine. So if we net work, it equals work for the compressor plus work for the turbine. If we express the work for the compressor as inlet minus exit, so we have m dot H1 minus H2 plus m dot H3 minus H4. And we can factor out the m dot. H1, we go 1.35 minus H2, 581.82. So that difference will be negative, plus H3 is 1418.84 minus H4 is 734.88. And that value is positive and greater than the first one. So we'll have a positive value then times m dot, and our m dot is 5.807 kilograms per second. And since we have kilograms per second in each of these terms, our kilojoule per kilogram, we'll get kilojoules per second, which is kilowatts. And when I do the calculations, I get 2,343.07 kilojoules per second or kilowatts. And then the heat addition is simply m dot times H3 minus H2. The other processes are isentropic, and then process 4.1 is Q out. So that's the only heat addition process. And I get that equals 5.807 kilogram per second times H3 is 1418.84 kilojoule per kilogram minus H2, which is 581.82. That gives me 4,860.5 kilojoules per second or kilowatts. And then finally, the efficiency just equals the network over Qn. And that would be 2343 over 4861 if I round it to the nearest decimal, nearest integer rather. 2343 divided by 4861. I get 48.20%. All right, well, that was very detailed, every step. The other problems will be more shorthand and just kind of go through the main steps. This one was cold air standard. The next problem is the same one, but using air standard. And the only difference really is that the isentropic processes, we use the ideal gas tables to find the enthalpies.